So here we stopped where we stopped last time, and we said that the least square technique can be applied to nonlinear function as well. And we give an example that if our nonlinear function is an exponential function, then this is what we end up. We need to solve this nonlinear equation, so we need another numerical method way to do that. And then once we know the b, then this equation is a nonlinear equation in terms of b. Then I go back and solve for a. Okay, so that makes this is not really practical, and we need to go for another approach. Just to recall, we have finished working with linear model. So if I have a linear model like this, yi and xi, okay, so we have here numbers yi and xi, and then y is equal to a0 plus a1 x. Okay, so if this is my x, my independent variable, my y, so I have points like this. So these are the points. I'm trying to find the best fit. Okay, and then from this we found, okay, to find a1 and a0, your a1 is basically nothing but n, which is the number of points. This is n. Okay, multiplied by the summation of multiplication of xi, yi, then minus summation of x of I times summation of y of I, everything divided by n, summation of x of I squared minus summation of x of I all squared. So basically, once you have yi and x of I, then you have to find x of I, yi multiplied. Okay, and then you need to find this is the summation here. So you find summation of y of I, which is this one. You find the summation of x of I, which is this one. You find the summation of the multiplication, which is this one, and then you will find x of I squared, which is this value, and of course at the end here you find the summation of all these numbers. You add all of them. Okay, and then you find x of I and take its square. Then you will find a 1, and then after that you will find your a0, which is equal to the average value of y. So this is the summation. So we need to find the average value of y minus a1. A1 is this constant that we just found times x average. So this is how we deal with if my function or my data fits a linear model. Now, what if it does not? We have seen in the previous slide that that's not really practical to solve the nonlinear equations directly. So what we do? Let's see here. So this is one of my nonlinear functions, and this is an exponential function. So this is like, for example, charging a capacitor. As we know from circuit, that when we charge a capacitor, actually we are getting an exponential function if it's charging like this. If it's discharging, it will be there is a minus here. Okay, so what we want to do here basically, and this is what we will do in all other equations, we will do what we call linearization. I will linearize this. I will change this from a non-linear equation into a linear equation in that format. Y is equal to a0 plus a1 of x. And then I will go and solve for this constant the same way we did, and then I will go back to the original equation as we will see here. So let's see here this equation. If I take the len of both sides, okay, so if I take the len here, this component becomes len of a of 1 plus len e to the power of b1x, which is b1 of x. Okay, so here I take the len of the dependent variable and then len of the nonlinear function, and then I can say that this ln y is what we call y star. And this ln a1 is my constant a1, and this is b1 is my a1. Okay, so now I have linearized the function in that format, and now my graph is like this. So this is the y-axis is ln y, the x-axis stays as my x, and here the slope is my b1, and the intersection is a0 or ln a1. Okay, so I go and I forget about this equation completely now, and I go and solve for this. And to do that, if my data was given as yi and then x of I, so what I need to do here, I need to find, instead of y of I will have y star, which is equal to what? To ln yi. So I come here to all the data points here, I will take their ln and I put them here. Now I fit a linear model. So your y becomes ln y, and here I will find a0 and a1. Once I know a0 and a1, I can find the original value that I want, which is the a1 and the b1. How? Just equate this to ln a, and then take to e to the power of both sides, then I find a1, and basically a1 is nothing but b1. Okay, so this is how we deal with an exponential, and we'll do the same approach for any non-linear function. The approach is, in simple language, trying to linearize the model. Let's have another example. Let's assume here we have the power equation, which is here y is equal to a2x b2 to the power of b2. Okay, so what I will do here, I will take the log for both sides. If I took the log here, this becomes equal to this. Okay, so this now becomes your y star. This is your constant. This is your a1, and this is your x star. So here now we have an x star. So now if my data, there's a question here says, let me see, the log, there is a base of 10. Yes, this is the base of 10. Yes, exactly. Okay, so if I go back to my data here, I will have the original data, which is my yi and my x of I. This is my original data. I will find y star, which is log of y. And then I will find x star, which is log of x. So I need to calculate these values. So if this is my values here for yi and x of I need to find log of y. So I take all these data points and find its log, and this become my y star. And then do the same thing for the x value, and this become my x of star. Now I know x star, y star, then I will solve for this, becomes a linear equation. And this is the drawing of my linear equation, becomes a linear equation. Okay. Once I know the find a0 and a1 exactly using the same equation we use for the linear model, I can go back, equate a1 to log of a2, then take the 10 to the power of both sides, I can find a2, and b2 is basically nothing but a1. Then I can go back here and I fit the model. Let's see another equation. This is called the saturation curve. Okay, the saturation curve, this is, we see that in many practical aspects in electrical engineering, like for example, for a linear inductor, a real inductor, it follows this, the pH curve or the current flux curve, it follows like this. So in circuit, we assume that the inductor works only in the linear region, but after that becomes non-linear, and you might cover that in some advanced courses in power engineering or in electronics maybe, or maybe in electromagnetics. Okay, so now this is my equation. I want to linearize this equation. Remember, always I want to put the equation as a equal to a0 plus a1 of x. So any non-linear equation, I'd like to put it in that format. Okay, so this equation is equal to, as you can see here, y is equal to a3x divided by b3 plus x. Okay, so I want always to put it in that format. So what I will do, I will take the inverse of both sides. So this becomes 1 over y is equal to b3 plus x divided by a3 plus a3x, which is 1 over y is equal to, this becomes b3 plus x divided by a3 x. Okay, so this becomes b3 divided by a3x plus x divided by a3 of x. So x will cancel. Okay, so now I will have this is as y star equal to, this becomes your a0 plus this becomes your a1 x star. Now, what is y star? Y star is nothing but 1 over y. What is x star? Is nothing but 1 over x. Okay. Now, what is your a0? Your a0 is nothing but 1 over a3. And what is a1? Is nothing but b3 over a3. So from this you can find, so this is your a0, this is a1. From this you can find a3, and from this, once you know a3, you can find you can find b3. Okay, so again you need to manipulate. So in the exam I might give you a totally different function, totally different nonlinear function. So you need to play with it to make it linearized, do all the necessary conversion in the data. Originally you will have x and you will have y data, then you need to do some changes in this so that you will put the equation in that format. Okay, so here it is, the equation, and here is the y star. This is the curve. Comes a linear curve. Let's have an example here. Okay, so in this example, this is my xi and yi. Okay, and this is my function. Okay, so I need to linearize this first, have the data, find the constant of the linearized function, then go back and find the original function. As simple as that. Okay, so here, if I take the log as I just did, I'll just refresh your memory. I will take log of y equal to log of everything here, which is a2 x to the power of b2. So this becomes log y, okay, equal to log of a2 plus log of x to the power of b2. So this becomes log of a2 plus b2 log of x. Okay, so this is your equation. So this is my equation. So this is my y star, sorry, this is my y star equal to, this is my a0 plus, and this is my a1, and this is my x star. So what I need to do here, I need to expand this now, and then I need to calculate my x star. What is my x star? Is the log of x. I need to find my y star. This y star is also the log of y. Now I have the new x and the new y. Then I need to find other values, which is x star times y star, which is x times y in the original linear model, and x star square. And then find the summation, find the new a0 and a1, and then go back and find a2 and b2. Let's see how we'll do this. So this is the derivation of the formula I just did, and this is now my linearized model. Okay, and this is the original value, x of I, y of I, and this is x star and y star. These are the values. We start from here. Log of 1 is 0, log of 2 is 0.301, log of 3 is equal to 0.477, etc. Okay, and then we go for the rest. It says here, let's see if here, just curious, could we have picked log to bases other than 10, like log to base of 2? You could, but there is no need for that. I mean, you will get the same value. There is no difference between the two. But log x, log base of 10 is the most common one. It's much easier to calculate, and your calculators. So it's this is why. But you can do any base. Doesn't really matter. Okay. Now we are set. Now I will forget about these values now. So I don't need these values. Okay. Now we will have, so now this is my complete table. This is, you have to do it, okay? As I said, these values now, they are not relevant to me. Now this is my new x and this is my new y for the linearized model, okay? And then I multiply x times y, so multiply this times this, and take the x squared, and the end here we have the summation. This is, I'm summing all of these values. So here, for example, 0.301, etc. This is the value of the summation, and this is the value of everything. Now, after I set my table, I can now start finding my A1 and A0. So your A1 is basically the n, which is here. I will let me write the equation: n summation of x of I star, of course, summation of x of I times summation of y of I, and this is divided by n summation of x of I square minus summation of x of I all square. Now what is n? Is the number of values, 1, 2, 3, 4, 5. So this becomes 5. Excellent. What is the multiplication of x of I, summation of x of I star, y of I star? There is a question here. It says y x of I equal to, not that, no, actually this is the summation of all of this is not a variable. This is the summation of all of n. So this is the summation of n. This is the summation of n equal to 15. 1 plus 2 plus 3 plus 4 plus 5. This is 15. Okay. Okay. So summation of x of I times y of I, x of I times y of I. This is the summation, which is 1.424 minus summation of x of I, which is 2.079. I will answer your question once I'm done with the formula. Times summation of y I, which is summation of y of I, which is 2.141 divided by, again, n is 5, times summation of x of I square, which is 1.169 square. Sorry, there's no square here. This is xi squared, so this is 1.169 minus, this is the one that has the square, which is 2.079 square. So if you do that, you will find this is equal to 1.75. Once I know this, I can find A0, which is nothing but the average of y star minus A1, the average of y star. Okay, so now the average of these value, I will take the average of these value. Let's take the average. This is equal to 0.4282 minus A1, which is 1.75, times the average of, sorry, this is x, the average of x star, which is average of x star. This is the x star, so the average of this, which is equal to 0.41584, and this will give me a value equal to minus 0.334. Okay, so I found now A0 and A1. Okay, before I move, let me check the questions if you have any. Yes, I guess. What happens if after we do, okay, I will come to this. We get 0, 0 case. do we use the special case for linear regression? What happens if after we do log of x of y, we find them? Yes, yes, that's a very good question. Okay, this is a very interesting question. He said that what happens if when I after take the log, imagine if I take the log, this becomes 0 and this becomes also 0. So it means that it goes through the origin, so we go for the special case. Thank you very much for bringing this question. Okay, now let's move on. Okay, so this is my original model. This is my linearized model. Now this is my equation. This is my A0 and this is my A1. Okay, remember that the model is like this. This is log y equal to log A2 B2 log of x. So I need to find A0. So I will equate my A0, which is minus 0.334 equal to log of A2. How to find A2? So A2 equal to, take the raise the 10 power of each side. So this becomes 10 to the power of minus 0.334, and this is equal to 0.463. This is your A2. Okay. Now I need to find B2. Now when I compare this with this B2 is nothing but A1, which is equal to 0.1.75. Now my model is ready. My model, original model, which is y equal to A2 x to the power of B2 becomes equal to 0.463 x to the power of 1.17. So this is my model. Okay. So this is how we can find the nonlinear model after that linearization. Let's have another example, and after this example, I will stop here because we will go through another concept or a different function, which is a polynomial. Okay, a polynomial is a very general, it's a little bit big concept, so we will leave it for next class. Okay, so let's see here. Now, a question you might ask: how do I know which function to fit? Because there are tons of nonlinear equations. Okay, one way to do that is by knowing the physics of your problem. I kept mentioning this a couple of times, that how do I know which formula to use? Understanding the physics. This is why it's very important for someone to use numerical method is to understand the physics of the problem. And you are supposed to use these techniques in your problems as an electrical or a computer engineer. So you have to understand the physics. You have to understand, okay, this phenomena will give me what type of curve. As I mentioned to you earlier, I mentioned two examples. Example of a capacitor. We said the capacitor, and we know that from circuit, basics of circuit, that when we charge a capacitor, it follows an exponential function. And when you discharge a capacitor, it is also an exponential function, but the exponent is a negative. Okay, so this is something we know from our understanding to the physics of the problem. When I talked about the saturation curve, I said this is how a nonlinear inductor behaves. So again, you as an electrical or computer engineer, you work with inductors. So you know that a linear inductor will have a fixed value of L, but a nonlinear inductor will have a variable value of L, depends on the value of the current and the flux because of the saturation. Okay, so from the beginning, when you deal with something like this, you know exactly which formula to use. You don't need to go and search. So that is when it comes to the practicality of application of these functions. Now, for the sake of argument, if I don't understand the physics, like for example, in the simulation assignment, it will be released to you maybe before the end of this week or early next week. you will find that I gave you a data that I don't tell you from where we get this data. Okay, so I don't know which physics it follows. So I don't know which formula to follow. Yes, maybe I can draw it and look into it. Okay, but again, you will see that nonlinear functions sometimes they behave in a similar way. Like for example, the exponential or the power of x, they have somehow little bit of similarity. So you might not be able to judge by just looking to the data point. So what is the best way to do that? Is to find the r square, exactly like what one of you just mentioned that here, that if we use the r square, does the r square exist in yes, the r square does exist, and you need to calculate the r square. And the r square is the criteria that you can tell which one is better. The closer to the one is the better the model. Okay, so and you will see this, you will test this. I will ask you to test two different sets of data against four different models. Okay, and then you will find the r square for each of one, and then you will find that okay, this data fits which one, which model better. Let's go to this example now. So here it says a charged capacitor with a 20 volt. So a capacitor originally was a charge with a 20 volt connected to a linear circuit, which I don't care about. And I have a switch open, so that charge is there. And then I switch on the switch, meaning I connect the capacitor to the circuit. So the capacitor start to discharge, and I started calculating or measuring the voltage across the capacitor every 2 seconds. And this is the data, and this is the how they look like. Okay, so as we know, the capacitor fits an exponential decaying function. So we want to find this exponential function, and we want to estimate the discharging of the capacitor. We can even estimate the R and the C, because we know that the discharging is following the time constant, which is 1 over RC. Okay, so we can even estimate the charging, the time constant of our system. Okay, so our model that we want to go through is a nonlinear model. Okay, and this model, this nonlinear model is in the form of y equal to a to the power of e to the power of b of x. Okay, and you will find that later on that b is negative. We will see this as we will derive the formula. But this is the function that we want to find. Okay, now this is my independent variable, which is t. This is my dependent variable, which is v. So if I want to rewrite this instead of terms of y of x, it will be like v is equal to a to the power of e power of b t. So this is my y value, and this is my x value. Okay, so let's move on here. So I want to linearize my model. Okay, so as we know, for this, what I need to do, I need to take the len function. Okay, so I will take the len for both sides. So this becomes len of v equal to len of a e to the power of b t. Okay, so this becomes equal to len of a plus len of e to the power of b t, which becomes equal to len of a plus, actually, this becomes b of t. And this is len of v. Now, remember, I want to have this in terms of v is equal to a0 plus a1t. Okay, so this is your v star equal to len of a plus bt. So from this, you can say that your A star is len of A, and your A1 is B. Okay, as simple as that. So let's go back here. So this is my table. So this is my T. This is my the value of X, originally X. This is the value of Y. So this is my Y star. Okay, and this is my X squared, and this is my X times Y star. I don't need to change the X. The X stays as it is. Okay, so now if I draw the new Y, our X versus the new Y, this is what I get, a linear model. Look here, this is the previous one. It was a nonlinear function. Now when I do the linearization here, this is what I get, a straight line. Okay, so that is now the line I am working with. And now I found here the summation for all values, summation of T, summation of everything that I needed here. Then I need to find my A1. So what is my A1? A1 is equal to my N summation of the multiplication of X times Y star, which is this one. Or I will call it T times len V minus the summation of T times the summation of len of V. Okay, divided by, again, N times T squared minus summation of T all square. Now what is N? Is the number of lines, which is 1, 2, 3, 4, 5, 6, 7, 8. So this becomes equal to 8 times summation of T, my T, which is equal to this, times len V. So T times len V. So this is the summation that I'm looking for, which is, I don't need to put the summation here. So this is becomes 1.739 minus the multiplication summation of T, which is the summation of T, which is 56 minus 56, times the summation of Y star, which is this one, which is 18.347, divided by, again, 8, times the summation of T square, which is 560 minus the summation of T, which is this one, all square. So it will be 56 all square. So if you do the calculation, you will find that is equal your A1 minus 0.09934. Okay. Now I need to find my A0. My A0 is equal to the average of this. So I need to take the average of all of these values. I have to find the average here. Okay, you see all the values. So this becomes equal to 2.293 minus A1, which is this one, minus 0.09934 times the average of the T. This is the T, so I need to take its average, and its average is equal to 7. So this is equal to 2.989. Okay, so I'm done with finding A1 and A0. Okay, now if I fit, let me just to make it clearer for you. Okay, so this is the line that I fit. This is the linear function. This is, I use Excel here actually, just to confirm that my answer is correct. Okay, so I mean, this is something you can do in the quiz, but you can't, of course, report it. Just if you want to make sure that I'm just giving you a hint here for those who are attending the class today or listening to the class after that. In the quiz, when I give you something like this and you want to make sure that you are doing it right, then you can go and Excel and find the trend line and find the function and compare it with the function that you have. So this is a way that you can compare your answer actually. So we look here to the linear model. It is minus 0.000993, which is this one. X, this is your this is your A1, and plus the constant, which is 2.9888 here, which is if you take four decimal or four significant digits or three decimals, it becomes 2.989. So the linear model I found is correct based on this data. Okay, so this is. But here it's very important to do the conversion correctly here. If you messed up this, then everything else will become wrong. So you have to be careful when you do the conversion. Okay. So now this is my model, y equal to a e to the power of x. Okay. So we know that b is nothing but a1, which is equal to minus 0.09934. And we know that a is equal to nothing but e to the power of a0, which is e to the power of 2.989, which is equal to 19.86. So this is your a, this is your b. So your y is equal to a, which is 19.86, e to the power of minus 0.09934 x. If you want to be more realistic, this is v actually equal to 19.86 e to the power of minus 0.0994 times t. So this is the exponential function of the decaying of your capacitor. So if I use the Excel, this is the function I got, and here is the. You'll see there is slight differences. It depends on the significant digits that you are using, but it looks for us very close to this formula. Okay, so basically you learn now how you can generate a function in the trend line in your Excel sheet. Okay, let me see your questions now. Okay, so why would there be an error with A, the initial condition? Okay, that's a good question. Okay, as your colleague saying that if I substitute, and this is a very good question to be honest with you. Okay, so your colleague saying, okay, now if I come here and find V of 0, if you do that, V of 0 is equal to 19.86 e to the power of minus 0.09934 times 0. Okay, so this becomes 1, so it's 19.86